Alright YouTube, hello, thank you for watching. Decided to sneak one more electronics video in. I'm waiting on some chemistry stuff to arrive here, so I'm in a holding pattern. So I decided to kill about 12 hours time with this project yesterday. Put a fan on there. It's a 60 millimeter 12 volter. Probably draws, oh, I don't know, probably about 250 milliamps. It is one of the higher output fans. But yeah, I put it on a piece of G10 FR4 board that I use for pretty much everything. I've said this in many of my other videos. It's impossible to work with, but it always gives you fabulous results after you're done dealing with all the fiberglass in your fingers. Well, it was kind of a pain in the ass to do this because I had to get down in the fins to mark it. You know, you can't get really, when you're setting something on that's got so many standoff points, the probability of getting the standoff points aligned are pretty much zero. Somehow I pulled it off. I was able to mark the inside of these fins down in there with a pair of calipers, just kind of at a weird angle. But got it on there perfectly square, man. Just pulled the wires down through the cutout in the back of the unit there, where the pass transistor wires go through. I just used the existing standoff holes that were inside the unit here, and then just spaced this off and ran the screws back through, longer screws, in order to hold this heatsink back on the back like it was, so that way I didn't have to make any more holes for it. I did run into a bit of a clearance issue here getting the son of a bee in, because I was in probably too much of a hurry and didn't spend enough time thinking about it. I just flew by the seat of my pants on it. Went to get it in there and I said, oh shit, that ain't gonna work. I forgot there's not a lot of clearance there on those transformers, but I just had to cut the standoffs down. It's a little awkward getting in and out, but you know, it's completely doable. So there's just an LM358 on it. Some of these cheap little things here, you know, I'm not a super big fan of these, but you know, you can buy these guys here through All Electronics. They're really cheap, and they pretty much always have stock. So if you need any, you know, inexpensive connectors like this, screw down connectors, which I typically don't like to use, All Electronics is a place to go for that, and probably I think they're in Van Nuys. Stuck an Omron 12 volt relay on there, used up half of LM358 8-pin dip. Gonna check it out here and see if I made any mistakes on it. Somewhere, yeah, somewhere there's a cap. I'm just gonna kind of kludge him in there. I think I'm gonna have a long hard talk with my neighbor's cat because it just looked like there was a flea on my hand. I don't take well to fleas, never really have, because once you get them in your house, it's not really a pretty sight when you get them like I've seen people have them already. Solder that 22 mic right across that Zener diode. So anyway, I had this thing back in the cubby hole there. I leave them on for days and days. When I pulled it out the other day, this thing here was so screaming hot. It was kind of crazy. Really doesn't get any airflow back in the cubby hole there. So that was the point of this. Everything's done there. This resistor soldered directly across the IC pins. That's the hysteresis resistor. And the reason I do that is because sometimes I like to change it. You know, that's the best I can put it. You can calculate exactly what value needs to be in there based on what temperature you want this to cycle off and on at. More to the point, when it turns on, to cool it down, what temperature you want it to have to fall back down to in order to turn itself off. That's the hysteresis. So the turn on and the turn off point of the fan is not the same. That's what this resistor does. And like I said, calculating it is not far-fetched. I mean, it's pretty simple to do, but sometimes I just don't do that. So that's why I solder them across the IC. So that's what that mysterious 680K resistor is right there. That is hysteresis between pin 3 and pin 1, which is the output of that LM358, back to the non-inverting terminal, which is pin 3. I think that pin goes down. Yeah. Well, lights come on. That's good. Fan's not on. That's always a good sign as well. Put the DVM on ground there. At this point I should have, I can see what the hell I'm doing here. Should have, yeah, it's an 8.2 volt Zener, 8.3 on the Zener, and this is the schematic of it. That's all it is. Half of an LM358. There's still 3 unused pins, which are going to be pin 5, 6, and pin 7 is going to be the output of the other op amp in there that's not used. There's the hysteresis resistor. Here's your reference point set up by this divider here. This 47 and 43K 1% sets that reference level at like 3.917 volts. So when this point here drops below 3.917, this will go high. When the negative terminal falls lower than what the positive or the non-inverting terminal is, that will trip the op amp to go to a high state. So right here's the 100K NTC thermistor, which is somewhere around, I think, like 42K at the temperature that I wanted, somewhere in that range anyway. So at 45 degrees C, the voltage on this divider here is going to be 4.05 volts. So 4.05 being greater than 3.917 is going to keep this in an off state. So once that temperature starts to go above 45 degrees C, this voltage here starts to fall down. When it falls down to the 3.917, this will toggle high and turn the fan on. Pretty simple, man. Op amps, I mean, they're the most beautiful invention ever made. I couldn't even tell you. Should have about 3.917 on pin 3. The fact that we don't have exactly 3.917 kind of tells me something. It kind of tells me that pin 3 of the op amp is pulling current, and that's why the voltage is not as high as what the calculator says it should be, because there's input current going into the amp. Some op amps have a greater input current than others, and this LM358 seems to have a pretty significant input current to it. So pin 2, if I can do this without spiking my op amp out. It's nice when you have clips, but you know, even if I had a clip, I mean, who the hell could who the hell could get the clip on that op amp anyway? So pin 2 should be something greater than 3.917, and it is. It's 4.8. As the temperature rises up, that voltage is going to fall. So it's definitely warming up, but you can see it's got a ways to go. It's got to drop something under a volt before this fan's going to turn on. So we got a waiting game here to see if I made a mistake on this board. It's barely kind of warm, but it's by no means hot at all. So I'll let it sit here and toast for about an hour or so. It probably would help things if I put a load on this, put a mic and a speaker and stuff like that to warm it up a bit. I just kind of picked 45 degrees C randomly. I mean, there's really no method to the madness there. Just the fact that the fan comes on at some point before the damn pass transistor melts down. So it's creeping down slowly, about a millivolt at a time. It's probably going to be hard to see, but that thermistor is actually mounted right here. There's a screw going into the heat sink that, well, it holds down another ring terminal, but I lifted that up and put the thermistor underneath that one. so it's almost at the top of the heat sink. I mean, it was really too much to try to get the thermistor anywhere else because there's just no damn room inside that heat sink. So just FYI, just in case somebody sees this video that didn't see any of my previous shenanigans in electronics, you're probably wondering what in the name of God is inside that Madison. Well, we have dual power supplies in this Madison. So you might be asking yourself, well, why? Well, I just wanted to see if I could do it. That's why it's there. And actually, it was a bit harder than what I anticipated. I think probably the hardest part about it, well, it's probably about equal, was number one, fitting the damn thing in there. And number two was the modifications you had to do in isolating power supply lines to do what I did. Because this power supply here actually drives SSB, and this power supply here actually drives AM. And that's the way I intended it to be. But what I didn't count on was how much of a train wreck I was going to get into with isolating power on the board between the AM and SSB, which all came down to basically the area in here with some stuff that had to be isolated. And then the power supplies, this is the this is the screwed up part. The power supplies had to be tied into the AM upper sideband, lower sideband switch because your finals, the voltage to them is switched through here. So when I flip this to AM, if I remember right, yeah, when I flip this to AM, you see this relay pull in. That takes this power supply off the SSB power, not really power source, but the power supply, and flips the power supply here through the modulator chip to supply the finals with power for AM transmit. I have no idea. I don't even think I'm not even sure I said that right, but it's a complicated damn mess, I'll tell you that. So we just wanted to see if it could be done. How long it took me to do that, hell man, anyone's guess is as good as mine. If you do it wrong, I can tell you what happens. When you key it up on AM, yeah, 25 watts of power coming out of the back of the radio on AM. If you make a mistake, that's the best I can tell you. But yeah, that way I got a separate SSB power supply. Well, it warmed up a good bit, but obviously not enough to kick on a fan. Nope, 4.255, that's got to drop down to about 3.8 volts for the fan to come on. Now I can tell you this, if you think the top is something, boy, you ain't seen nothing yet. You ain't seen nothing yet. You gotta see what the bottom looks like. It's beautiful, don't get me wrong, but you know, you just need to see what it looks like. This is something insignificant I did here. But actually, when I told somebody what I did, they said, that's a really good idea. And I thought, okay. I isolated the power switch on the front of this so that the power switch, this cheesy little switch, isn't switching all the power to the unit. So I ran the power switch into a relay and left the relay switch all the current to save on the life of the power switch. So you can see when I put power on it, it reverts it. I don't know if it's opening or closing. I can't tell which way this relay goes. But that's allowing power to the finals for SSB operation. This one here would be pulling on too. On power up. This is the Madison that I put what Bournes considers to be a locking pot on. Just in the interest of science, I wanted to see what they were all about. All it is basically a dual pot. So when I flip this guy out, the pot on the front is active now, and when I push it back, the pot on the back side of this is active. So it's kind of a weird concept. It's technically not locking. I'm not even sure how they arrived at locking out of that, other than to say, well, can't even really say that. So I don't know what the theory was behind that, but some high-tech redneck shit. That's the best I can put it. See where this thing's at. Down to 4 volts basically, so still got like 200 millivolts to go. It's pretty warm, I can say that. Transistors aren't warm. Should say the transistors aren't hot themselves, but the heatsink sure is getting there. Make sure it's falling. Well, maybe it's not falling. The heatsink's just kind of, I think I hit a plateau where the heatsink's just dissipating it, and it's not getting any hotter than this right now, which is a good sign, which means that the heatsink is shaking it off. But that doesn't really help me test my fan because this voltage needs to drop. Try setting a 100-watt light bulb over it, see what that does. I seem to have kicked it in the pants. It's really amazing how sensitive these damn thermistors are. Just moving that light a couple inches like that. This would be a lot quicker if I had, if it was using power in the unit somewhere. There, we're getting close. Got about 70 millivolts to go, and something should kind of happen here. There we go. I want to see how long it runs for, that way I know if I need to adjust this hysteresis resistor. Not too bad. Not too bad as far as on time goes. That cooled her down pretty quick. Still above warm, but not super hot. So that resistor probably could come down in value just a slight bit. That would keep the fan on a little bit longer, and that would run this temperature down a little bit lower, but you know, it doesn't need to be. Just the fact that it comes on and cools it down is what's important. If that resistor were much higher, above 680K, say like megs, like 2.2 megs or something like that, or a meg or what have you, anything considerably higher, the duration of that amount of time that it took to turn the fan off would be much shorter. So if you don't put a hysteresis resistor on, what happens is your turn on and your turn off point is the exact same voltage. So it'll just sit there and chatter the damn relay back and forth without hysteresis on it. So all that resistor does is determine how much lower that voltage has to go before it turns itself off. So it just kind of differentiates the switching points so that they're not the same, if that makes any sense. But yeah, there we are. So anyway, that's about the end of the road there. So hey, I appreciate you watching my video very much today. Take care and have yourself a great day.